Lab number 16, working with memory and cohere in the Haystack Framework. Creating a generative AI question answer pipeline with retrieval augmentation using Haystack. For Haystack, we will be using in-memory document store, BM25 retriever, prompt node, prompt template, and cohere command model. The goal is to create a generative question answering search system that can use large language model through prompt node with the prompt template. First sequence is working with memory. We have done the installation of Pydantic 2.5.2, a specific version of Pydantic. Then let's import the required modules. And this is the interesting part. Our model is chat cohere. All the default settings will be taken. Prompt will come from prompt template. We need to understand it in a bit of detail. It will be crafted, it will be created from temp messages, where system means the preamble, you are helpful chatbot. Message placeholder will include the messages from the history, means previous conversation. And human input, that means our question will be placed here, the input placeholder. Then we are defining this memory, conversational buffer memory, to hold our messages. Then load memory variables. Now memory variables, the name of the variable is history and it is empty right now. The list is empty. There is no message, no previous interaction with the model as far as our program is concerned. Now the chain is very interesting to watch. The first element of the chain is runnable pass-through assign history equal to runnable lambda load memory variables, and specific item we are loading from the memory is history, which means in short I can define this as I'm loading the content of the history where all my previous interaction with the model are stored. That goes to prompt, which will create the prompt using this template, which means the preamble will be configured, will be set, the message from the history will be placed here, and the human input will come after the history. So this template will be used for the prompt and that will go to the model. So this is chain, how we created the chain with three components. First component history, second component prompt using a template, and then third component model. So I'm defining my input as input variable, hey, I'm Ram, and response, I'm invoking the chain with inputs and printing the content. So what I expect from the model is quite simple response, hey, hello Ram, how can I help you today? So this is the response from the message chatbot. I want to display this what message I have received, and I want to save it also. So first let's save the context, including the input plus the output. Output will be part of the message what I received. That means response.content, which is exactly this one, which is nothing but this content. Hello Ram, how can I help you today will be stored as output along with input. So this will save it. And if I want to now if I load memory variables, I'll see the history variable but not empty, with proper interaction which I just now had with the model. So I'm printing this, and now you can see that history variable with human message, the content, then AI message and the content. So you can see that the proper interaction with the model is stored in history. Now this history will go based on this chain, the history means this complete, whatever I selected will be part of my next request to the model. Means because I'm putting it here, that will go to the prompt and then model. So prompt will include this messages here, chat placeholder, variable name history. So this history will be placed, and then I ask a follow-up question. Input, what's my name? So this will be the follow-up question. So we have this history and a follow-up question, and I'm invoking the chain. Therefore what I expect is it should tell me that your name is Ram, and that's what you are getting. This is how this memory concept works in all the playgrounds. This is a programming concept team. This is a feature of programming implementation of the business logic, not the model. These few cells explain the concept of how the memory is implemented in platforms where you ask follow-up questions from the model. Is there anything else I can help you with? So point to be noted, you have to implement the business logic for handling the interaction with the model. Now whether you store that in memory, or you store that in session variables, or you store that in a database, that's your implementation. In skillpedia.ai, I store them into the database so that even if you drop, even if you disconnect, you can start from where you stopped when you join back again. So this is the memory concept. Then working with Haystack. Ensure that you restart the kernel after installation, because it will remove some packages, it will install specific package. Kernel restarted mandatory, given in bold. So installing Haystack, I'm running this installation. After installation, ensure that you restart the kernel and start from the next cell. So let me restart the kernel. It is restarting. Wait till the restart is complete. Now done. So we'll start from here now. Initializing the in-memory document store. Let's create a question answer system by initializing a document store. A document store stores the document that the question answering system used to find answers for your questions, and we are using in-memory document store. Let's initialize our document store from Haystack document stores. Import in-memory document store. Document store is defined with use bm25 equal to true. So it will pull the documents from bm25. So these are warnings or optimization things. You can simply ignore them. But yes, our document store is registered, is ready. In-memory document store is the simplest document store. It requires no external dependencies and is a good option for proof of concept and learning. The document store is now ready. It's time to fill it with some documents. Let's fetch and write the documents. It's time to fill it with some documents. We'll use this Wikipedia pages, 7 Wonders of Ancient World, to pull the content from this Wikipedia page and fill that in our document store. The data is pre-processed and uploaded to a Hugging Face 7 Wonders, and this is the Wikipedia page, and this is where it is uploaded. These are the contents, the ID and the content on the Hugging Face. So we are using data sets, load data set, and this will pull the data set from this account, which you can see here, this particular data set, and we are going to load it. So this is the data set we have. This loading the data set from Hugging Face. Now we are initializing the retriever. Concept of retrievers have been discussed in detail. Let's initialize the BM25 retriever and make it to use in-memory document store we initialized. Haystack nodes, like in LangChain we have chains, here we have nodes. So BM25 retriever is defined, initialized, and then define a custom prompt with Cohere API key. This is the prompt template we are using. Here we are using the documents plus the question and the response what we expect from the model, from the Haystack. After that we are ready to ask questions. Define the pipeline with the retriever. In Haystack the building blocks are pipeline. Like in LangChain we have chains, here we have pipeline. So pipe equal to pipeline, name can be anything. Add node, component is retriever, name is retriever which is defined here. Retriever defined here, this one. So name is this retriever with the document store and top k equal to 2. Input is query, that the question will be asked by the user. Then another node, component is prompt node, name is prompt node which is defined here, prompt node. Input is the retriever. That's it. The pipeline is ready. Now we can ask questions. This question will go to query. Then this will be sent to the prompt node to create the prompt, because prompt will be crafted from the prompt template, and the output will be parsed and in proper format output will be displayed. So let's run the pipeline with pipeline.run, pipe.run. So this is one simple question we are asking, and we'll get response from the document store, and this is the response. That's the purpose of Haystack. That's how Haystack works. More questions you can try with these examples. Memory, agents and Haystack. In this session we'll understand the concept of memory and agents, structured data and output parsing techniques, data loaders, Haystack and use cases. Some of the topics are already discussed, so will be skipped from this session. Working with memory. Most of the large language model applications have a conversational interface. An essential component of a conversation is what? That you can refer to the messages, the interaction you have earlier in the conversation. So it is being able to refer to the information introduced earlier. Like what I have been doing always, the refer to my 3 slides on that day, refer to my topic discussed, refer to my demonstration. That is memory. A conversational system should be able to access some window to some window of past messages directly. We call this ability to store information about past interaction as memory. LangChain provides a lot of utilities for adding memory to a system. These utilities can be used themselves or incorporated seamlessly into a chain. How it works? A memory system needs to support 2 basic actions: reading and writing. Every chain defines some core execution logic that expects certain inputs. Some of these inputs can come directly from the user, that is user query, but some of these inputs can come from the previous interaction, that is memory. A chain will interact with its memory system twice in a given run. 1. After receiving the initial user input, but before executing the core logic, a chain will read from its memory system and augment the user inputs. Second, After executing the core logic, but before returning the answer, the chain will write the inputs and the output to the current run to the memory, so that they can be referred to in future runs. To understand it in a better way, let's look at this figure. The initial user question, the moment user question is entered, it should read the messages from the memory, and it will fetch the past messages, interactions, and along with the question plus the past messages will go to the prompt using prompt template. That's what you have seen during the demonstration, past messages and the question. This was our history and this was our user input. That will go to the model. Model will respond. Then we may include output parser. And once the message or the history is created properly, we send this response to the memory by write function. So we write this to memory. And then that message is displayed to the user. This is the step-by-step process how the memory concept works. This shows how to add memory to an arbitrary chain. Right now you can use memory classes, but you need to hook it up manually, and this is the same screenshot of the code lab. Conversational buffer memory, message placeholder, chat prompt template, runnable pass-through, runnable lambda, chat cohere, and this is our prompt crafted with the history placeholder along with the preamble and the user question. That will make the proper prompt that will go to the model. Now we are creating chain with 3 components. First is the history that goes to the prompt, and then finally that goes to the model. And this is the question input. Hi, I am Ram, invoking the chain just to see the prompt. Then saving this context, verifying it whether it is stored in the history or not. You can see the output. It is stored, human message and AI message, and then you are asking a follow-up question. The entire interaction with follow-up question goes to the model, and you receive response from the model with the proper correct answer, the response to your follow-up question. Now I will request you to try lab 12 also, sequence number 3 and 4, where follow-up questions were asked. You cannot do that follow-up questions related to lab in the Jupyter notebook without understanding the concept of memory, which I just now introduced. That will be the task for you. After you complete, you attempt sequence 3 and 4 of the developer lab, that was lab number 12 or what, where we learned how to write code using playground, and the lab 9 and the corresponding version of Jupyter notebook of the same lab. In that lab, in sequence 3, if you go back, you will see that you are asking follow-up question in the playground. So I expect that you enhance that program using LangChain and memory, and you are able to ask follow-up question even in the Jupyter notebook. That will be the challenge, so you will get extra time for this. Please complete that lab 9, sequence 3 and 4 in Jupyter notebook format. Next topic is agents. Official LangChain documentation describes agent as some applications will require not only a predetermined chain of calls to the large language models or other tools, but potentially an unknown chain that depends on the user input. In these type of chains, there is an agent which has access to a suite of tools. Depending on the user input, the agent can then decide which, if any, of these tools to call. Basically, you use the large language model not just for input output or text output, but also for decision making. So agents are the language model that derive decision making. Agents help language model to derive decision making. More specifically, an agent takes in an input and returns a response corresponding to an action to take along with an action input. You can see different type of agents which are better for different use cases. Here the reference is given, the link is there for you, and spend extra 15 minutes on this also. If the name is changed, because things are changing fast, if it is with a different name, explore that also. Tool. A tool is capability of an agent. This is an abstraction on the top of a function that makes it easy for large language models and agents to interact with it. For example, Google search. Toolkit is a group of tools that your agent can select from. More on text splitters. There's something that was incomplete yesterday, that's always there, so that is in this session. So chunking data. Once you have loaded documents, you'll often want to transform them to better suit your application. The simplest example is you may want to split a long document into smaller chunks that can fit into your model's context window. When you want to deal with long pieces of text, it is necessary to split up that text into chunks. Ideally, you would want to keep the semantically related pieces of text together. What semantically related means could depend on the type of text you are dealing with. We have different type of splitters for that reason. Like one is recursive. It splits on a list of user-defined characters. You cannot add metadata, but this recursively splitting text recursively serve the purpose of trying to keep related pieces of text next to each other. Second is HTML. It splits on HTML specific tags, and you can also add metadata. So split text based on HTML specific characters. This add in relevant information about where that chunk came from based on HTML. Then markdown specific characters. You can also add metadata. It split text based on markdown specific characters. This adds in relevant information about where the chunk came from based on the markdown. Then code, Python, JavaScript specific characters. There are 15 different languages supported. So split text based on character specific coding, specific to coding languages. 15 different languages are available to choose from. Then token, where you split the text on tokens. And the last is character, a user defined specific character. One character, recursive and character. The difference is here we define a list of characters, and here it is a single character. User defined character, split text based on a user defined specific character. So that's a type of splitters we have when we use a text splitters, depending on the kind of text we are dealing with. How it works? At a high level, the text splitter work as following. Split the text into smaller, semantically meaningful chunks, often sentences. Start combining these small chunks into larger chunk until you reach a certain size measured by some function. Once you reach that size, make that chunk its own piece of text and then start creating a new chunk of text with some overlap to keep context between chunks. That means there are two different axes along which you can customize your text splitter. One is how the text is split, and second, how the chunk size is calculated. Haystack and its use cases. What is Haystack? It's an open source Python framework by dissect for building custom apps with large language models. It lets you quickly try out latest models in natural language processing while being flexible and easy to use. Community has helped shape Haystack into what it is today. It is a complete framework for building production ready NLP apps, and this is the page of Haystack, landing page or introduction page. So building with Haystack, imagine your data is in flat files or databases and you have different models to work with: OpenAI, Hugging Face, Cohere, Azure, Amazon SageMaker, whatever models you want to use. Haystack offers comprehensive tooling for developing state-of-the-art NLP systems that use large language models such as models from Cohere, models from Falcon, models from OpenAI and others, and transformer models. With Haystack, you can effortlessly experiment with various models hosted on platforms like Hugging Face or Cohere, or your local models to find the perfect fit for your use case. What you can build with Haystack? You can build semantic search on large collection of documents in any language. You can build generative question answering on a knowledge base containing mixed type of information like image, text and tables. Natural language chatbots powered by cutting edge generative models like Cohere. An LLM based Haystack agent which is capable of resolving complex queries. You can build information extraction from documents to populate your database or build a knowledge graph. In Haystack, we have components like the way in LangChain we have chains. Here we have components. At the core of Haystack are its components, which are fundamental building blocks that can perform tasks like document retrieval, text generation, or summarization. A single component is quite popular already, powerful already. It can manage local language models or communicate with hosted models through API. And then we create pipelines here. Pipelines are connecting tools. Pipelines are powerful structures made up of components like retriever and reader, connected to infrastructure building block like document store, for example Elasticsearch, to form complex systems. Haystack offers ready-made pipelines for most common tasks such as question answering, document retrieval, or summarization. But it's as easy to design and create a custom pipeline for NLP scenarios that are way more complex than question answering. Haystack also use agent. Same definition, same concept. Make use of large language model to resolve complex tasks. When initializing an agent, you give it a set of tools, which can be pipeline components or the whole pipelines. The agent can use those tools iteratively to arrive at an answer. When given a query, the agent determines which tools are useful to answer this question or to this query and then calls them in a loop until it gets the answer. This way, it can achieve much more than extractive or generative question answering pipelines. Output parsing, prompt instructions and string parsing. This is a helpful way to format the output of a model usually used for structured output. Two big concepts here. One is instruction for formatting. An auto-generated prompt that tells the large language model how to format its response based off your desired result. Second is the parser, the method which will extract your model's text output into a desired structure, usually JSON. This is example of Haystack, what I demonstrated in the lab. BM25 retriever, prompt template, answer parser, prompt node. This is a RAG prompt coming from prompt template. Here we are specifying related text, that is documents, and the question, which are queries, and the answer. This is a model to respond with based on the system prompt and chunks and the question. Now we are telling the model what is your answer about this. So this becomes the prompt node. Then pipeline, as I explained earlier, and the asking question from the Haystack, like running the pipeline with query where we have the question. So this question will be filled here in place of query along with the retrieved document. So therefore you will get more grounded response based on the system prompt, given context and the question. You will expect a better answer, more grounded answer, and auditable answer. Now we have two framework, LangChain and Haystack. Which one to use in what cases? Both are equally good, but yes, there are trade-off involved and you'll have reasons to choose one over the other. So let's discuss that part. LangChain use cases. Complex NLP workflow. For multiple NLP tasks like text generation, summarization, translation in a single workflow, it's better to use LangChain because it provides flexible ways to chain these tasks together. Custom conversational agents. Agents tailored to specific tasks or domains. LangChain allows you to build and configure these agents effectively. Task automation. By automating repetitive text-based tasks such as drafting emails or generating reports. Integrating various APIs. LangChain can interact with multiple language models, APIs, OpenAI, GPT, Cohere, etc. Experimentation and prototyping. Not to use cases. When it is not recommended to use LangChain. For example, if you are creating a simple single task application, there is no point using LangChain. For example, sentiment analysis, then LangChain might be overkill. Or heavy duty information retrieval. LangChain is not specifically optimized for large scale information retrieval tasks where specialized framework like Haystack might be more appropriate. Or resource constrained environments. LangChain's flexibility and feature set might introduce overhead that is not ideal for very resource constrained environments. Haystack use cases. Document search and retrieval. Haystack excels at building search systems that can retrieve relevant documents from a large corpus based on a query. This makes it ideal for enterprise search, legal document search, and academic research. Second is question answering systems. A system that can answer questions based on specific set of document. Haystack provides a robust tool for extractive question answering system. Knowledge base and frequently asked questions. Haystack is well suited for creating dynamic FAQs and knowledge bases. Pipeline customization, enabling the integration of various components such as retrievers, readers, and rankers. Scalability. Haystack is designed to handle large data sets and can be scaled to meet the needs of enterprise level applications. Haystack not to use cases. When you are dealing with general NLP task, it's not recommended to use Haystack because Haystack is specialized for search and retrieval. If you need to perform a variety of general NLP tasks like text generation, summarization, or other things, then other framework like LangChain might be more suitable. Or simple applications, or real-time conversational agents, or limited data scenarios. In any of these cases, you prefer not to use Haystack. LangChain might be better in such cases. So in short, LangChain is ideal for complex NLP workflows, custom conversational agents, and task automation, whereas Haystack excels in document search and retrieval, question answering system, and scalable knowledge bases. That's all for this session. Thank you so much, team.